In this video, we'll take a look at what it means to describe a line in 3 dimensions using vectors. And then we will look at the alternate forms and just see how similar those forms are to the ones we developed for lines in 2 dimensions. And then we'll look at some other geometric properties. So let's get started. So recall in the vector form, we need a point that the line passes through. Any point that it passes through will work. And also, we need the direction in which the line is moving. And that direction, of course, is given by a vector. So if L is the line passing through, and let's say we have our point, let's just call it P0 with coordinates x0, y0, z0. So if L passes through this point with direction vector, and again, we'll use the same notation as we did previously, but again, just add that third dimension to indicate that we are in 3 dimensions. So this is our point, and this is the direction vector. So then the vector equation or the vector form of the line L is, and let's write it down. So you may recall we're using the letter R, and it is a vector, and it depends on this parameter T, and it's of this form. So let me write it down symbolically and then simplify. So the first thing we do is we have to find the position vector that goes from the origin to this point. But a vector with an initial point at the origin, its component form, well, in fact, let me write it down symbolically like this. So this represents our position vector going from the origin to my point P0. And then we add to that all the possible scalar multiples of my direction vector that will essentially span or generate the entire line. So T times V, right? So now let's write these down and do our vector operations and simplify. So the position vector OP0, since it starts at the origin, the components of the vector are simply x0, y0, z0, but now we use our angled brackets to indicate that we're referring to a vector, right? So that's the vector OP0, and then here are all the possible scalar multiples of my direction vector. So A, B, C, and though not needed, if not stated, it is implied that T can be any real number, right? So our parameter T, for us to generate the entire line, it has to be any number from negative infinity to positive infinity, right? And then we can use our vector operations to combine these two vectors into a single one. So we're going to distribute the t and then add the corresponding components. And here's our vector form. It's x0 plus at, comma, y0 plus bt, comma, z0 plus ct, right? So that is our first form, right? And this is the vector form of the line in 3 space that passes through this point and in a direction parallel to this vector. And again, just before we go on to the other forms, I just want to make a point. Suppose, just let's say you had the need to work in 4 dimensions and you wanted to do this process for a line in 4 space. All you would need is a 4th coordinate in your point, and a fourth component in your direction vector, and this would still be the same. And the vector algebra would still be the same. You would just now have a fourth component in that vector form. And that's I like to refer to it as the scalability. In other words, this process or this procedure or this concept scales to any finite dimension. Yeah, pretty cool. All right, so that's the vector form. The parametric form is where we essentially write down in this case, three equations, three separate equations, one for the x component, one for the y, and the third for the z. So if I simply write down x equals x0 plus at, comma, y equals y0 plus bt, comma, z equals z0 plus ct, then this is the parametric form, right, of the same line. So this is our parametric form. Right, and again, it's parametric because again, each equation, right, is in terms of this. You can literally think of the variable or the letter t as the variable that defines all the possible points, because we're using all the possible values of t. And in fact, in the future, we're going to see just how important this t is and how you can really, it makes you really, gives you the ability to treat these things as actual functions. So we're going to talk about vector functions. That's going to be even cooler, right? Okay, so we got the parametric form, and then the third form now is the symmetric form. And because all of the, so if we assume that all the components of the direction vector are non-zero, so basically an easy way to say it is this: if our direction vector is not the zero vector, which means that A is not equal to 0 and B, well, actually, no. What I'm saying in parentheses is actually a stronger statement here. So let me take this out and write something that truly is equivalent. If the magnitude of the, no, I can't say that either. So you know what, let me just state what I'm going to state in parentheses without trying to get too fancy. So if A is not equal to 0, B is not equal to 0, and C is not equal to 0, then what that allows me to do is to solve each of the three equations for t. So from my x equation, I will get that x minus x0 over A is equal to, and then solving for t from the y equation, I'll get y minus y0 over B. And then finally, solving for t from the third equation gives me z minus z0 over C. And then all of these being equal to each other like that, you know, this is referred to as the symmetric form of the line. Right? So symmetric form. And we saw these three forms in the two-dimensional case. In 2D, we have other forms, but those other forms depend on the quantity that we call a slope. We really don't have the concept of a slope once you get to 3 dimensions or higher. So that's why we rely exclusively on these forms that depend on the vector, right? And again, each form that we have, just by inspection, we can identify the point, right? Which would be the x0, y0, 0. And we can also identify the direction vector, which would have components A, B, C. All right. Now, before we get into an example, a fairly simple example illustrating all of this, I do want to make an interesting distinction about lines in 3 space versus lines in 2 space, right? Now, in R2, Lines may intersect at one point. So lines may intersect at a single point. Oh, come on, single point. Or they may be parallel, so they may intersect at a single point, or be parallel, or they may be identical. So you might have two equations that might look differently, but when you plot them, you end up getting the same point. So we might say, or may be identical. And those are the only three possibilities in R2. So in other words, graphically, it means if I graph the equations of two lines, either I will see this or this, or I will see, and just for emphasis, I'll do this, right? Or I'll see something like that. So if I give you a pair of lines in R2, at least, well, one of these things must be true. Either one point of intersection, no points of intersection, or technically infinitely many points of intersection when the lines are identical. In R3, these things are also possible, but there is a fourth possibility, right? So in R3, lines, let me say it like this. So in R3, non-parallel lines, so lines that are not parallel, right? So non-parallel, non-identical lines, meaning so that they're different. So non-parallel, non-identical lines may still not intersect, right, at a point. So may still not intersect. And let me illustrate how. So I'm going to sketch my right hand orientation of 3 space, so that we're familiar with this. We have our X, we have our Y, and we have our Z. Now, and here I'm indicating just the first octant. That's the region where all the variables are positive. And again, when we were going through this previously, I mentioned that, you can think of this as a portion of your room, whatever room you're in right now. The floor would be the XY plane, right? So down here, so that's the XY plane, and that would be your floor, right? And then if I essentially raise the floor, or if I look up a certain number of units, what I would have here is another plane, which we could refer to as your ceiling, right? So this would be the ceiling in your room, right? And again, unless you live in some fancy avant-garde room where at some point, things get tilted and slanted and whatnot, your ceiling is not going to intersect with your floor. In fact, you could say that they are parallel, right? These planes, you have the XY plane, and then you have another plane, a certain number of units above it. These never intersect. So what I could do to indicate that it is possible to have lines that are not parallel, right? Not the same, and they still won't intersect, I could do something like this. I'm going to take my favorite marker and I'm going to draw a line on the floor. And then my parents are going to yell at me because I damaged their fancy hardwood floor. And then, as out of revenge for being punished, I'm gonna look up at my ceiling and say, you know what, I'm gonna draw a line up here too, and I'm gonna draw the line like this, right? And there you go. So what we have here is we have a pair of non-parallel. They're certainly not moving in the same direction, right? They're definitely not the same, right? But they don't intersect, right? So these lines, so let me just call this L1 and this one L2. So L1 and L2 are said to be skew, right? So L1 and L2 are said to be skew lines, right? And this is a property that cannot exist in R3. I'm sorry, R2, right? We basically, we don't have enough dimensions for some things like this. If you have only 2 dimensions, then, we call this a trichotomy. 3 things, one of which must be true, right? Here, we have a 4th possibility, and it's when you have what are skew lines, right? And it's not difficult to figure out, like in R3, which of these 4 things are actually occurring. And we'll see it with examples, right? Either in this video or in subsequent work, right? So now let's look at an example working with these lines in R3. So we'll use one example to illustrate several different things. So let L be the line passing through, and here are the 2 points, -3, 4, and 1, and -1, 2, 0, right? So that's all we know. We have a line L, and it's passing through these 2 points. So let's part A. Let's find the vector equation of the lines. Let's do the vector and the parametric and the symmetric. So we'll find all 3 standard forms of the line L. Well, here we're not just given 1 point, we're actually given 2 points, right? So you can use any one of these as the terminal point of your position vector from the origin. In other words, you can call this P0 or you can call this P0. It doesn't matter, right? So I'm just going to use the first order triple. I'm going to let that be my P0. So let P0 be the -3, 4, 1, and then I'll call the other point P1, right? So and P1 be -1, 2, 0, right? So we have the 2 points. Let me just label them so I don't have to do the ordered triples anymore. So what we're going to do, wherever the origin is, right, we know it's going to be somewhere else because neither of these points represent the origin. It's going to be somewhere else. What I'm going to do, what I'm going to do, I got very southern there. I am going to form the position vector O to P0, and then I'm going to use the vector from P0 to P1. That's going to give me the direction of the line, because the line passes through these 2 points. So I can use this as my position vector. So let's say the origin is there. We're going to find OP, and then I'm going to let me use a different color here. Maybe make that one dotted, and I'm going to use that as my vector V, and then I can apply the result that was stated earlier. So OP0 is the vector. Again, going from the origin to this point, the components of the vector are simply the coordinates of the point. And then V will be the vector p0 to p1, right? And that will give me the direction of the line. Just like how in your previous work with lines, you needed 2 points to find the slope. Well, if you're not given the direction vector of the line, then you're going to need 2 points on the line, 2 distinct points on the line to find that direction vector. So let's see, what's the vector that goes from p0 to p1? Well, using our head minus tail, it's -1 minus -3, 2 minus 4, 0 minus 1. So here's our position vector. Direction vector of the line. So this is 2, -2, -1. And now let's write down start with the vector form. So our R is OP0, so this vector, plus any scale, or I should say every possible scalar multiple of V. So 2, -2, -1. And again, I'll just say that T can be any real number. And then let's combine it into a single vector. So here is the vector equation of the line. So what do we have? -3 plus 2t, 4 minus 2t, and then 1 minus t. Right? There we go. Right? So this is our vector form, and then the other two forms are easily found. The parametric form simply state the x, the y, and the z as separate equations, and collectively they form the parametric form. So x is -3 plus 2t, y is 4 minus 2t, and z is 1 minus t. This is our parametric form. And then solving each of these, which we can do, right? Because remember, the symmetric form isn't always possible, because if for instance there isn't a t, like if one of these components of our direction vector came out to be 0, which it's possible in some cases, right? You might not have, well, you won't have a t to solve for. So the symmetric form doesn't always exist. It exists when all the coefficients of t, right, each coefficient of t, I should say, is non-zero. So solving this for t, I'll get x plus 3 over 2, and that has to be equal to the t from the middle equation, which is y minus 4 over -2, which also has to be equal, and that's the symmetric part, to the t from the third equation, which in this case is z minus 1 over -1, right? And we can leave it in this form. If you wanted to do things with the negative sign, you could do it, and so forth. But I'll just go ahead and leave it and identify this as the symmetric form of our line L, right? So there we are. We have all three forms. Now, here's another interesting question. So here we have this line. Does this line, so does L intersect, let's say, the YZ plane? Does that happen? If it does, so if so, at what point? Right? At what point, right? So we have this line, and we know it extends indefinitely in a certain direction. That direction is defined by the position vector here. We know the point that it passes through. We now want to know, does that line intersect with the YZ plane? Well, let's see. Let's think about it. What fact do we know about the YZ plane? So think about it. In the YZ plane, what we know for sure is that x has to be equal to 0, right? So x is equal to 0. Well, looky here. We have an equation specifically for x, right? What's interesting about the parametric form, it's almost that you can analyze each of the variables, right? Our coordinate variables, x, y, z. We can analyze them independent of each other in some sense because we have three separate equations, one for each variable. So if x must be equal to 0, then we can actually figure out the value of t that will make the x component, right, equal to 0. And then once I know the t, I can figure out the y and the z, and then that would give me the point. So to answer the first part about does it intersect, we have to see, is it possible for x to be equal to 0? So we would write -3 plus 2t is equal to 0. And this is an equation. If it has a solution, then the answer is yes. The answer to the first question is yes. And we can see that this easily gives us a t value of 3/2. So this we would say, so the logic is this: since there exists a value of t such that x is equal to 0, L does intersect the YZ plane. So L does intersect the YZ plane, right? But we don't know the actual point. We only know what happens to the x value, right? We know that that's 0. I mean, we didn't have to do any work. That's just how our coordinate system is defined. To figure out the actual point, we now need to determine what is the value of y when t is equal to 3/2, and what is the value of z, again, when t is equal to 3/2. So let's do that. So when t is equal to 3/2, y is equal to, now go to the y equation. Now use that equation to figure out its value. So we will end up with 4 minus 2 times 3/2. So this is 4 minus 3. We have a value of 1, right? So that's good. And then similarly, when t is equal to 3/2, z, what's my z value? Well, use the z equation. So you'll have 1 minus 3/2, which is -1/2. So that the actual point of intersection now is the point 0, 1, -1/2. So let's write that down. So L intersects the YZ plane at the point, and then we write our order triple, 0, 1, -1/2, right? And this process, right, this could be repeated for the XY plane. In that case, we would have to start by setting z equal to 0, and then following this procedure. And we could also do the XZ plane, in which case we would have to set y equals to 0, right? Let's answer one last question and say now, does L, right, does this line intersect the, let's say, x-axis? Right? So does this line actually pass through the x-axis, right? Well, let's think about what we know about the x-axis. So in the x-axis, right? So, or we could say along the x-axis, what must be true? Y has to be equal to 0 and z has to be equal to 0. So we would have to ask ourselves, is it possible, like, is there a value of t that would make both y and z simultaneously equal to 0? Well, how do we figure that out? Well, we set the y equation and the z equation both equal to 0, and solve and see if we get the same value of t. If we don't get the same value of t, then we're going to end up getting contradictory values. Hence, these two conditions cannot be satisfied. Therefore, the line never intersects the x-axis. So let's write down the y equation. So we have 4 minus 2t is equal to 0. Well, if you solve this, we could see that t would have to be equal to 2, right? So t would have to be equal to 2 in order for the y value to be 0. Well, what about the z value? Well, the z equation is, I was going to write the letter z again, but the parametric equation for z is y minus t. Now, that would have to be equal to 0. Well, that can only be 0 when t is equal to 1, right? So let's say you were to think of t as time, right? Well, after 1 unit of time, the z value would be 0, right? Which means it would actually be in the xy plane. And then after 2 units of time, then the y value would be 0, but then the z value would be something else. It wouldn't be 0, right? So since these are not equal to 0, so so since 2 is not equal to 1, L does not intersect. So L does not intersect the x-axis, right? And I think that the interesting thing about all of this is, notice we never had to even to attempt to sketch the line, right? We were simply, once we were able to find the equation, we could then use essentially the definition of certain regions in 3 space to answer these questions algebraically, because that's what we did here. We used algebra as our sole tool to answer these questions about intersections, right? So, and essentially what you're seeing here, these are procedures or skills or topics that you would study when you're studying what's called analytic geometry, as opposed to constructive geometry, where you'd actually use pictures and graphs and measuring and so forth. Here we're using algebra to answer these geometric questions, right? And that's what we want to do, because once we do our algebra well, we get a precise answer and we understand exactly what's going on. So with that, we're going to wrap up this video, and I will see you in the next.